Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Mojan Sohi.
Hey, Mojan, good to talk to you again. We were chatting the other day with a potential client, and she mentioned that they wanted to create a RAM model, a reliability and maintainability model is the kind of the way she phrased it.
Mm-hmm.
And we're listening to, here's a bit of this and that, and overview what the project might be and all this good stuff. But at one point, it came across my mind, well, why do you need a model? Just build the thing so it doesn't fail and you're fine. And, what's the model for? And I asked her, is it for this or this? But it dawned on me, there's like 8 or 9 other reasons maybe of why we do reliability modeling. So
Yes.
I thought, sometimes you got to pick the tool because it's for some purpose. And I'm quite sure they had thought through it, why they wanted this thing, but it wasn't clear to me when she was talking. So I thought I'd ask. And she didn't, she came in with an answer that is I'm not always comfortable with. And I thought I'd chat with you a bit about why you do modeling. But it's if the modeling is only to say, we meet the spec, independent of whether the system actually does it or not, then that's kind of dangerous. So I don't think just modeling and doing, a bunch of assumptions and all the other good stuff to get whatever answer you want. I didn't think that's a useful way to use a model, but I didn't really get the impression that that was why she wanted it, or not that level of detail. She wanted it to be accurate as possible.
Yes, I think that's right. She wanted it to be accurate as possible. And, it was to an actual practical purpose of being able to plan for their service intervals and, proactive maintenance plans, which is great. That I think that's a legitimate, it's not just modeling for the sake of modeling. They are actually thinking about proactive maintenance and how to do it in a smart way, which is great. I think that I'm curious actually what your experience is, because I think that there are many industries that could benefit from this type of modeling, as opposed to just like, well, I keep thinking about some cars, because it's like every 3,000 miles you got to do this, and it doesn't matter how you're using your system or your vehicle, right? So it's I think that is you could be serving your customers better and saving a lot of money if you think about not doing that and doing maintenance in a smart way.
Well, yeah, cars. I think some dealers just hope that they cross-thread the oil filter drain plug so that they get to charge a whole bunch to replace all these parts.
Right.
There's some of that, but it's easier with fixed time schedule. Back in the 50s, 60s, we didn't have the sensors. We didn't have, to some extent, auto manufacturers had or should have known the environmental uses. And if you use it on a racetrack versus using it going to church once a week, the use conditions are very different, and the wear and tear in your engines. It's people who've known for decades and decades that taxis that drive 24/7 with occasional stop for fuel and oil drive 500,000 miles just fine. Whereas
Yes.
cars that are, a short commute and run to the beach once in a while they have more problems. And it's so I think the modeling and feeding that back into your maintenance plan so that it's dynamic. And you and I both look for it with vendors is like, give me a model that says if you're going to run it at this temperature, here's what you got to do. Here's the concern. If you run it in this environment, then here's the issues and the type of failure mechanism, the model for it. That's real information, and we can deal with it. And then, like you said, is then make decisions about maintenance schedules and types of activities and what to focus on, what to measure, stuff like that. I think the model overall has to have a purpose. What are you going to use it for? What are you going to do with it?
Yes, yes, exactly. And you know what I think it also the exercise of working on creating the model is itself also useful because it forces some questions to be asked about assumptions and what data is available and you know how reliable is that data and
Yeah, there's that. Yeah.
how you know and what else should we be doing you know to improve our understanding of the performance of the you know of a component or a system for example. And I think that's a good exercise, you know, as opposed to, I mean, you and I both have seen where uh more often than not you know a number is provided by the vendor of like this is our MTBF and then that's it. You know, there's no no necessarily questions around, you know, what does that mean
Where
for
did it come from
from
and
my
what is it?
product, where did it come from? How did you get it? You know, what conditions were assumed? How do those conditions compare to what my product is doing? You know, and unfortunately it's kind of just left at that and that you know gets taken into account. But when you're working on actually creating a model for something like proactive maintenance planning, it forces those questions, I think, to be asked, which is very useful. It's a very, very good exercise.
It is, and it's part of it is thinking about, well, what is likely to fail? It's different than an FMEA, yet it's the same thought process. All right.
Mhm.
If in order to estimate how long something will continue to work, is it's the other side of that question is, well, what's likely to fail? And then you're into failure mechanisms. And all right,
Yes.
well, this wear pattern get to critical in how long, how many cycles, how often is it used? You know, all those other aspects of you can address it once you know what you're dealing with. And so working with design teams or with previous products and failure analysis or whatever is, but you have to ask the question first. If you just take the box and go, oh yeah, it's going to be 80,000. Okay, we'll stick that in there and drive on. You're just flying blind, in my opinion.
Yeah.
Um, so it's talk to the team and the questions and what do we know and what don't we know. And sometimes we get a bad reputation because we always talk about how is it going to fail. There's that.
Yes. I have been in situations where in some of the jobs that I've had where, you know, as I go up to the design engineer's desk, they just look at me and that you could just see the blood drain from their
It's right.
face.
Oh, here comes the
What
vampire.
happened now?
Yeah. What did you break
What
today?
did you break?
Yeah. Now
Yeah,
that's one
exactly.
aspect. It's interesting though, is one of the cautions with doing a model of, say, a new design or new system is we're often looking at will it last 5 years or 10 years or 20 years? We're looking at the longer term type aspects. Yet our first prototype doesn't start up or the green light doesn't turn green or something like that. The modeling often doesn't include the early life failures, the misassemblies, the,
Yes. Yeah.
just the design was wrong and those kinds of issues. So it's in interfaces. Let's say it's not assembled correctly and or just the timing or the software is not talking to each other as it should. Those are harder to model. And yet,
Yes.
one of the things that I like is, and I saw it in the presentation we saw the other day, was, oh, we'll add a 10%, management buffer over here. We'll just we'll account for what we don't know over here. Give it some
Yeah.
margin. And
Yeah.
that's a
Yeah.
decent practice is that
Yeah,
it
you give it some buffer.
yeah, give it some margin, some buffer and stuff like that. But
Yeah.
a whole other reason we're touching into the design thing is as you start probing into the design and what works and what doesn't work and what do we know and don't know, I think there's two ways the development team, the design team needs that information is, well, what's the thing that's going to limit the performance? What's going to fail first? And what can we do about it if it's not
Hmm.
going to meet the overall target? And rather than waiting until you have a bunch of prototypes and then discover it again, or you have a suspicion that this is the bad actor in the overall system, but you're not sure. And we don't have a lot of
Hmm.
information or other information. Now you feed that forward into the testing and what we're going to measure and monitor, maybe pull it out as a subsystem or or a component and test it itself. But you got to know what you're looking for. And if you can do something about it without having to go do testing, go ahead and do it while it's easier earlier in the program.
Hmm.
And a model can help us weed through I always like to say, even a pencil has like 1,000 ways it can fail, right? But only one
Another
of them
good one for a
matters.
t-shirt. If anyone's keeping track of the t-shirt comments, like I think we're at four, four,
No,
four good t-shirts now.
oh no. Oh bother. At some point, we're going to have to make some t-shirts.
Oh yeah, no, it's gonna happen. I'm just waiting. I think if we rack up a few more good ones, and then it's happening.
Oh, you want to?
Just
If we're at a dozen, we'll have to make a calendar.
oh my God, that's such a good idea. Yes, I love that.
Okay. Oh, we can branch out into screensavers and all kinds of stuff. We can just have too
So
much
many
fun with it.
options. Possibilities. The
Yeah,
possibilities are endless.
that's it. And also ways it can fail. But the
Yes.
idea is that, to some extent, I think design teams, and I've heard this from designers, is we're trying to make it work. Okay, great. If it doesn't fail, isn't that the same objective? And they look at me like, no, I don't. I hate talking about failures. And I think part of it is it's because
Yeah,
they know as well as we do is that there are 1,000 ways this thing can fail. And a
yeah,
meteor
yeah.
hitting it is something that it's rare, and there's nothing we can do about it anyway. There's some failures that are just going to happen, and we're luckily they're pretty rare, so we don't worry about them. Yet there's others that are obvious. Oh, it's really not supposed to do that. Let me go fix that. But I'd say 895 of them are in that middle ground of, yeah, maybe. And we get to
Yeah,
maybe
yeah.
100 of those in a decent program to solve them. And I'm just thinking percentage wise, we fix the obvious ones and the safety ones. We should always fix the safety ones. And then there's a whole bunch of
Always,
others
yeah.
that are like, there's too many. Either we ignore it or we do the ones we can, or we triage them somewhere. And what's interesting
Right,
is that
exactly. Yeah.
a model can help you then sort out. I'm just thinking of a series system model. We got 5 blocks in it, and one of the systems is, I'm always going to pick on the power supply because they deserve it. Um, that's likely to fail. It's the weakest point in this thing, and our information and our testing or our field data or just our engineering judgment says that's most likely to fail. Well, that's great information, except what do you do about it? Do we get a different design? Do we improve it? Do we keep it cooler? Do we use, different filtering and
Hmm.
buffering on the incoming power? What do we actually do? And I think the model helps to focus on, well, we got to put resources on the power supply. And then at that point, the keyboard team and the monitor team and the CPU team are like, cool, we're done. Don't break it. know, we don't have to
Yes.
push the next, digit on the reliability. And I think that's one of the most useful things I've ever seen is where the program manager would look at the model and say, all right, power supply, you're the weakest link. Come back next week with a proposal of, what do you need to do about it? Do we need a different system? Do we need a different design? Do we need a different environment for it? What are the options and what does it cost? And until they become not the weakest link, they're on the hook. Because we can't improve the system if the weakest piece is still the weakest piece.
Yes. Yeah. They need to become yeah, yeah, yeah. I think I really like what you said about the program managers, asking or focusing attention and resources on this because oftentimes I feel like the um like this it's almost like a hidden skill set or a hidden gem that the program managers a knob that they can turn that
Hmm.
is in their power that is often underutilized. I think a lot of times um you know I think understandably, but a lot of times program management is focused more on timelines, which is fair, but
Hmm.
that's part of it. But this is like a really useful tool that they can have in their on their belt that can improve product integrity a lot if they focus on like, okay, what's the weakest link? Where's the data for that? what are we going to do about it, like you
Yeah.
said?
And the argument, I think, especially when it's a time-based project, right? We know we have to ship for the holidays, or we have a big conference, we got to launch it by that date, or whatever it is. There's almost always a time thing. I think they get taught in school that engineers cannot be trusted to deliver on time because they will always work on it as long as they possibly can.
Yeah, there's a fear of analysis paralysis.
There's a bit of that. Yeah,
Yeah,
just do it.
yeah,
And
yeah.
but one of the arguments in that realm to use a model like this is in that way where you focus resources is instead of each of your teams spending $100 each to try to solve a problem or make incremental improvements or improve their piece, even though it's more than adequate already, and it may even be unknown if you don't have the model, you're not tracking at say subsystem level. Let's put $1,000 on the weakest link so it can actually make progress. It's not dilute the resources. And what you get
Mm,
is you make progress where it counts the most earlier in the program, which saves you time. Instead of 10 people working, an hour a week on something, let's put one person for a whole day to solve a problem. And it moves forward instead of really taking way too long to make incremental improvements, many of which are not necessary. And instead, shore up the areas that really do need improvement so that you don't discover this late in the program and delay your program. You will have fewer problems if you focus. And I think they get it. I think most program managers understand it is we need to provide guidance and focus and appropriate resources. But I
hmm
see too many of them where they have a staff of very senior people with whole teams under them and they're all fighting for resources. They all want that extra new hire. They all want the more lab space.
mm,
And unless you have a model or some measure that's useful at the system level with breaking down to the subsystems, you're blind as to where the resources go. It's a gut feel is who's the better salesperson to get the resources. That's not in the best interest of the product and its performance.
yes, yes, exactly. And the model forces you to kind of think about, yeah, like you said, what is the weakest link? Where does it make sense to put the most amount of focus and resources on it, and um, get the biggest the biggest bang for the buck, basically.
Yeah, yeah. That t-shirt's been taken already. It's not mine. Yeah, so there's feedback to the design team to provide focus. There's where to focus testing or measurements and where are the uncertainties? What do we know we don't know now? And we got to sort that out. It also helps point out, we really need to fix that. And here's the failure mechanism. What can we do about it? Helping with maintenance and maintenance planning and preferably dynamic maintenance where it says, given your environment and use conditions, here's what you should expect. I think another one is the model part gives us a structure to compare test results to or even field data to. If we don't know what to expect and where the failure should be happening, it with some probability, and we get a stack of data, and we can do analysis on that and say, oh, it's this reliable. But was that expected or not? How well did we model is one feedback of real data. The other one is, did we even run the test right? If we're running a test on say, a power supply, and we expected that voltage overload would be the issue, but we only saw a completely unrelated failure mechanism. And this is a real story, is that I went back and said, did we actually have this thing plugged into a power system, feeding it with over voltage
hmm
and some spikes? And they go, oh no, that wasn't, that was too much trouble. We didn't do that. Okay.
Yeah.
That is where the issue was. That's what we're trying
Yeah.
to design to protect from. And no wonder it passed.
Yes.
You didn't
Yes.
test
Yes.
it.
Yes. Designing the test in such a way that you know is going to pass. Yeah, that's I've seen that before as well. It's a
Yeah.
kind of
Well, the guy
defeats
in
the
the
point.
lab says, well, it just fails when I do that.
Yeah.
Okay. If
That's
power,
kind of the point.
power
Yeah.
coming out of the wall does that on occasion, brownouts, spikes,
Yeah.
inductive loadings, all that stuff. And he goes, yeah, but our power is clean. Okay, well, that's the problem.
Yes. Yes, yes, exactly. Exactly. I think that the this I found I'm curious if you've had similar experience, but I found this portion of test design, and it's a slightly different topic, but
Hmm.
this portion of test design of like, well, do I really need to do that? Like, how representative do I need to make it is actually kind of part of the most challenging uh, uh, section of this whole exercise that I've seen in general within reliability. Is like you get to a point where like, it just becomes harder to replicate some conditions, and then people tend to want to say, "Eh, well,
Do we really need that?
do we really need that? Is that really necessary?"
Oh, I got a call at
Yeah.
10 o'clock at night one time from this
Mhm.
technician that was assembling prototypes to go into a series of experiments. And it was a sleep aid device, like a CPAP, I think it was called.
Mhm.
And it's supposed to be quiet, So if it has this whiny sound that sounds like a mosquito flying around your room,
Yeah.
even though it's not terribly loud, it was at a frequency that a lot of customers or patients complained about it
Yeah.
because it's hard to
Just
sleep when
loud
you got a
enough to be
mosquito flying around your
yeah.
face.
Yeah, yeah.
And so we brainstormed, how could that possibly happen? And we had, breakout stuff. We had all these stuff failures that we'd seen, and they did a bunch of analysis for and stuff like that. And one of the things that was a top hitter was that the bearings would get corroded because it's got moisture and all this other stuff floating around here, and these
Hmm.
bearings were corroding. And they thought, well, that's got to be where that noise is coming from. Nobody really knew. We couldn't turn it on and pinpoint exactly where the sound was coming from. And others were claiming it was the wind channels, the way the air moved through this device, and a bunch of other stuff. And so I get a call at 10 o'clock at night into this text saying, do I really need to put in these rusty, crody looking bearings into a brand new prototype? And I was like, yep.
Yep.
It's if we put in
Yeah.
clean ones, we don't really get to test whether the
Yeah.
corrosion is a factor or not. And he's like,
That's the point. Yeah.
uh,
Yeah.
it's just wrong for me to put it together. Like, please do. It's important.
Yes.
And it
Yes.
turned out to have
Yes.
nothing to do with it.
But you had to
We we
know.
had to know. If we didn't
You
know,
had to
we
know.
would
Yeah,
continue to be
exactly.
going, oh, just use different bearings. It had
Yeah,
nothing to do
yeah.
with it. But the modeling part, especially when you start involving environmental conditions, and you can,
Hmm.
well, brilliant reliability people can then see through how that environmental conditions will accelerate some failure mechanisms and not others. And it's from that modeling and that understanding of failure mechanism, we can say these test results are right on track. They're failing as expected, or they're failing too early, or they're failing too late. But we're getting what we expected. If we get completely different failures,
Hmm.
I always go back, was the test done well? But two is, why did it do that? What were the conditions that led to that? And then it's back to
Hmm.
the model to say, well, those conditions really don't exist in the real world. We don't typically
Yes.
take this 50-pound box and drop it on the floor 6 times before we get it in the test rack.
Hmm.
It's another true
Yes.
story.
Yeah, it's interesting because sometimes I feel like it's almost like two campaigns. Like one is that either they really want the test conditions to be easy,
Hmm.
like the tendency is to not make it the test aggressive in any way, just keep it, too not representative and just too easy. And then the other side of it is that sometimes the tendency out of because people want to be cautious, and they're like, well, I have to test in a really, really aggressive condition,
Yeah, worse conditions. Yeah.
worst condition. And so it kind of goes too far. And then, I actually had a similar discussion about this, a related discussion this week, where I was like, well, if we test under those conditions, then how do I, let's say it fails. what do I do with that information? Like, what does that tell me? Like, have I now cornered myself into a point where, I have to react because I said that this is my test, but even though it's not representative, but I said this is my test and now I have to act based on the results. And that would not be a very good situation, right?
Well,
And so,
some reactions are, yeah, it failed. We don't know when it'll do that in real life, so there's nothing we can do about it. Or if we have
well,
resources and
yes,
time, let's
yes,
make it more robust to that.
right,
It's
right.
not everything you find in a halt needs to be addressed with a change in the design.
Yes,
If
yes,
you
yes.
put it at such high temperature that all the polymer melts at 300 C, well, and the use case is at 40 C max, well,
Hmm.
yeah, okay, great. I'm glad nothing else failed.
Yeah, exactly. It's like
Yeah,
that's we found that that's the weakest link at that temperature. Great. Like, yeah, we can move on.
yeah.
Yeah.
But it's,
Yeah.
and I think one last one, and then we'll wrap this one up, is that oftentimes the modeling then can be validated or improved with test results or field data. It's the
Mm-hmm.
modeling itself then, especially if you're doing a family of products, you're going to do multiple iterations on this for the next decade. That model can become very valuable for design decisions, where to make improvements, as a way to fully understand customer feedback and field failures, what really is failing versus what we expected to fail. And one team I worked with years ago had been doing it for 15 years. They had a beautiful, complex
Mm.
model at failure mechanism level, and it accounted for all these different environments with the types of use, product use conditions, and such like that. It got to the point where they didn't make a development decision unless they modeled it first. Is it even worth doing? If we
Mm.
change this channel and this device, is it worth it?
That's
Does it
amazing.
make an improvement or not?
Yeah. That's the dream. That's everybody's dream, is to have a model that is that good to be able to know ahead of time.
Yeah. And
That's
it
amazing.
became, just the standard aid to decision making. And if it was beyond what the model could do, they'd build a bunch of prototypes and create a model, the elements they needed to feed into the model. It was amazing. So it can aid in decision making in what we listed as like what, 5 or 6 different ways.
Yes. Yeah.
Modeling in reliability is, yeah, it can be difficult. The data might be sparse or hard to get, yet there's always an option. There's always ways to do it. But if you're listening to this and you're looking at us like, why would anybody do a block diagram? That's nobody understands those things. And like, well, if you have to make decisions and you need to make comparatives, do we fix the power supply, which I always advise anyway, or the connectors or the CPU or something like that? A
Yeah.
reliability model really helps. If you're going to plan maintenance, a block diagram really does help. And I think Chris Jackson would talk about fault tree analysis. He loves those things. Um,
Hmm.
Yet it could be a very complicated model. It could be a very detailed Monte Carlo type simulation use kind of model. It could be all
Hmm.
kinds of ways. Yet it has to, at the end of the day, it has to help somebody make a better decision. And it's not just a checkoff list, and it's not just for fun. It's real business. So if you're listening to this and you do some modeling, or if we missed one of the many ways that they can be used and are useful for you, we'd love to hear those. Or if you like, what are you talking about? Yeah, let us know if
Yeah.
it didn't make any sense at all that good stuff. But we always look for comments and questions and ideas, and we pick them up from all kinds of places, including over at accendoreliability.com/go/SOR. A couple of ways to get in touch with us. Mojan and I and the other hosts of the show are available through LinkedIn and our about pages on Ascendo. So plenty of ways for you to get in touch with us. We should do a block diagram. If we do video ever with this, we'll do a little block diagram of all the ways you get in touch with us. And they're
Yes. Yes. I've blocked out. Yes, exactly.
including
Many
all
different.
of the infrastructure
Yes.
and all the IT fittings and all the servers that are involved.
Someone is going to ask us to model it, then you know that.
Oh yeah, yeah. You have multiple ways. We're not so good at smoke signals and telegraph and
Yeah.
fax
Or
machine that hasn't been
carrier
hooked up in a
pigeons.
decade. Yeah,
Carrier pigeons
they're
are
hard to
difficult.
find.
Yeah.
Stuff like that. But anyway, do
It's
get in
difficult.
touch with us if you
Yeah.
have a comment or a question, and
Yes.
you'd like us to chat through something. We always look forward to doing that. So with that,
Yes.
Mojan, I think that'll be it for today. Thanks for the
Yeah.
discussion.
Thank you. Yeah, that was great.
Yeah. Talk to you later. Cheers.
Yep. Talk to you later.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.